Hello to everyone. Thank you for having me here today. I'm Thomas Bertani, CEO of Oraclize. During this presentation, I will talk about the possibility of using Oraclize as it is today to provide some, a scalability solution maybe, or some options to communicate across chains. So this is basically an open discussion. It strictly depends on how the community of how people will choose to use the tools we have made available. So I will show you some examples during the presentation, and then we'll draw some conclusions. So first of all, I want to introduce quickly Oraclize in 5 minutes for those who have not heard of the project yet. So Oraclize has been around on the Ethereum mainnet for 2.5 years now. And it tries to solve the walled garden limitation. So the fact that when you have a smart contract in the blockchain, you are like in a sandbox. So you cannot really reach out to any external context, and it's impossible to get data from, say, web APIs, from a different blockchain, or from anything like this. So the way Oraclize does it is quite new because it separates like the oracle from the data source. So previous attempts, like before 2015, to provide blockchain oracles was all about trying to integrate existing providers of data with blockchain. Like, let's go to Yahoo Finance or to Bloomberg, and let's provide them an Ethereum node. Yeah, for sure. This doesn't really work in practice, I mean, in the real world. So what Oraclize tries to do is separating those two concepts and saying that the data transport layer, so whoever connects the external world, like the internet with the blockchain, doesn't need to be the data source itself. So the data source is like the external provider of the data, while the oracle is just an actor in the network that needs to deliver data that is integrated with the blockchain and that is capable of connecting the two different contexts. The application in our case on Ethereum, it will be a smart contract most likely, or a DApp in general. So here it's important to note that the oracle is like a crucial point of the architecture. So if the oracle tampers with the data, the blockchain application will just receive tampered data and will have no way to understand that the data is wrong. So this is why we need the oracle to provide some kind of guarantees, around the fact that it's behaving honestly and that everything is all right and the data is authentic, as reported by the external data source with no modifications. So this is what we call the authenticity proof. So the authenticity proof is a piece of data, some evidence, that Oraclize will always attach with the data when it is sent to a smart contract, so that you can verify that Oraclize is behaving as expected and that there is no malicious attempt to tamper with the data. So Oraclize is first of all, a technology that is blockchain agnostic. So it's not designed around, Ethereum only, but it's really, it enables the communication with like Ethereum, Bitcoin in a different way, with Eris, Monex, Rootstock, Corda, and other things. So it's really agnostic, and the core of the service is the providing the generation of those authenticity proof. So the key is, how do we get data from an external web API and send it around while proving it's authentic? So this can be done in different ways. There are today several projects that try to do it. For example, one is Towncrier, which uses technology listed in the middle here, which is the Intel SGX one. There are other techniques. Traditionally, Oraclize has been using TLS Notary, which is really, actually, if you're interested in diving into this, look for TLS Notary or Page Signer. And those projects, for the way they work, they rely on a trust line with Amazon. So it means that you need to trust Amazon in order to consider a TLS Notary proof valuable. And this is used by Oraclize basically to shift the trust and to move it away from ourselves to a different party, in that case, Amazon. However, even if you use technologies like Intel SGX, you are always trusting the provider of the technology. So in the case of Intel SGX, what it provides is some kind of hardware isolation for the execution of a process. So you can define a piece of code and say, I will execute it on a safe Intel CPU via Intel SGX. I can get a signature from Intel saying that the execution was safe, was done in a safe environment, but still you are trusting Intel because basically you have no way to verify that the context is really as safe as they claim it to be. Similar guarantees you get also with different providers. So for example, Samsung has something called Samsung Knox that they use in smartphones to secure the key store. Then you have, like, on Qualcomm devices, on most recent smartphones, you have a trusted execution environment from Qualcomm. And Android has also some software isolation techniques, like SafetyNet itself. The Ledger, I think there is a presentation right now done by Nicholas, the CTO of Ledger, in a different room. And the Ledger Nano S, of course, by default, by design, works as a wallet. But really, the way it works is it provides in a safe hardware environment the execution of any application, like it's an operative system. And you can use a technique called Ledger Nano S attestation to get a signature from Ledger saying that a claim coming from the device is really coming from there and saying that it's safe. So you can actually use the Ledger Nano S to execute any application and to prove that, according to Ledger, this is safe. So as you see, there are always some trust lines. So we might decide to trust Ledger. We might decide to trust Google for Android, Qualcomm, Amazon, Intel, Samsung, and so on. So why is this even interesting? Well, if we had to trust a single party, like Amazon, well, we wouldn't be here. We would just go to Amazon and ask them to run the blockchain. This will be much more efficient and realistic. What we are trying to do here is really providing some stronger guarantees by creating a structure which is similar to the one you see here. So it's basically different layers of protection. It's saying we don't want to trust a single provider, but the isolation techniques used here, all this sandboxing and securing of processes, which is called trusted computing in general, is something which is valuable and which can be used to extend the blockchain in a way which is flexible and which works today. So let's just use something like Oraclize in that case to generalize the problem and generate the authenticity proof based on the different techniques. So what happens is that you choose what claim you want to secure. Let's say the claim is the data fetching from a web API. Like you want to verify that Wolfram Alpha is really reporting a given result for the temperature in Paris. What you do is executing the data fetching within a trusted computing solution, and you generate an authenticity proof to back it. Then what you do is doing the same in with a different technology, and you keep doing it for all the technologies available. What you end up with is a sequence of proofs that together provide a stronger claim, because you will verify, you will be able to verify independently that the same claim is backed by all those parties at the same time, like Google, Amazon, Intel, Qualcomm, and so on. So if the data is wrong, it means that basically if the data is wrong but the proofs pass, it means that they are all compromising the data at the same time, in the same way, in a synchronized fashion, and they also compromise the Oraclize infrastructure, which is quite unlikely, especially when you compare it with the trust models we have today, even on the blockchain. So this is an example code that shows like the typical way in Solidity you would interact with Oraclize. So as you see, you just write Oraclize query, and you specify the API call you want to make. What happens is that Oraclize sends back a transaction claiming what the result is. Unfortunately, this is not very easy to read, but here there is the result of the transaction in the callback transaction. And what you see here is not just the result, but also the proof, the authenticity proof backing the claim. So the authenticity proof traditionally can be verified off-chain. So it means that you can monitor the network and see for the alpha million public queries backed by authenticity proofs we have, there is any one that doesn't pass. And you will see that there is none, but of course you can verify it independently. And this is the actual point of it. However, like 2 months ago, we released the Proof Shield, which is a new functionality which enables the verification of authenticity proofs on-chain. So it basically converts the complexity of authenticity proofs to something simpler without changing the trust model. So I don't want to dive too much into this right now because it's not the focus of the presentation. But the idea is that you can have a smart contract receiving the authenticity proofs and verifying them at a cost which is around 60,000 gas, so not much. And basically, you just enable it by specifying that you want the proof shield. So it's very easy. And then in your callback method, here you see somehow that you have a proof verification function you can call, and it will say like the proof is passing, the proof is not passing, and so on. So you can avoid like Oraclize pushing wrong data, even if you think we will be doing it once. Because of course, if you check it for the past, we have never done it. So, and you can verify it checking at the blockchain. So if you don't trust this claim and you think it might happen in the future, there is still the risk that Oraclize will do it once and then like waste his reputation. Still, with the proof verification on-chain, there is not a risk of it happening even once. So you can secure stronger, higher amounts. And with the proof shield, you can actually secure basically a different type of proofs, mostly all proofs. So in a nutshell, what we just said is that Oraclize can be used to fetch data from web APIs, and so you can get any data you like from a different context than Ethereum itself, like the web, the internet. Or you can, like get data from IPFS, or use it to, open a lock, send emails, all this kind of stuff that you can do with APIs. Something worth noting is that even if APIs are a central point of failure, data is always inherently owned by somebody. So if you want to check something like the temperature in Paris, you might say that a single provider is not trusted. So what you can do with something like Oraclize is just choosing like 10 different data sources and verify, what is the average or what is the data according to different players. So you can distribute the risk and as much as you like. Of course, the way you aggregate the data depends strictly on the type of data you want. So for the temperature, it's relatively easy. If you want a random number, things get much more complicated because you will never find a consensus on this. But it's not just web data, because this approach we just introduced with trusted computing backing the execution of the process can be used for different processes, not just for the data fetching. So something we released last year is this document. Let's call it a PDF, not a white paper, where we explain like a new approach to distribute untrusted delivery of entropy, basically, so on-demand and trusted delivery of entropy. And this is based on the Ledger NanoS specifically as the first implementation. So it basically generates a random number within a custom application on the Ledger NanoS that you can verify yourself. This smart contract can do it in the same way. And what happens is that you can verify that a single execution of the random number generator on a safe NanoS produced a given result, according to Ledger, for example. This is something that can be even more generic. So it can be used for any arbitrary off-chain computation we like. Like we define a piece of code and we say, can we get that authenticity proof for this process, for like our solidity function, or for our Python code, or for the engine of a derivative, or something like this. So it can be used via the computation data source, and this has been around for 1.5 years, and there are in the wild several projects using it for different reasons. So it can be used, as we see in the next few slides, also for providing interconnections between different blockchains, and also to scale up the blockchain by basically reducing the complexity that you keep on chain in the optimal case. So The authenticity proof on execution are exactly the same proofs we had before, but instead of securing the process of data fetching, which will be like one line of code saying fetch data from the web API, what we do is enabling the user to specify what the code is, so what should be executed. The way you do it is by defining a computation archive. So the archive is just you know, a zip container where you have to specify the execution context. So we use Docker to describe the execution context, not for the isolation itself. So Docker in the past has proven itself to be quite weak for isolation in general. So here we just use Docker because it's the de facto standard. So people just know how to write Docker files, and it's a good way to describe the execution context. Then what you do is distributing it to Oraclize or to some places where it can be verified, for example, on IPFS. And you communicate to Oraclize what is the IPFS of the code you want to execute. So the IPFS referencing the archive with the Docker file and the dependencies. So how does this compare with something like Truebit, for example? I just wanted to put this slide here, even if I explained also at DevCon 3 the same concept, because this is asked a lot, and I think Truebit is really an interesting project, but it's really not the same thing, so it's very different. So basically, the main differences between like a computation data source executed in trusted execution environments and Truebit is that Truebit needs the computation to be deterministic. So it needs the code to be written in a very specific way so that the verifiers can do it again and they can maybe challenge it on-chain if something goes wrong and if there is a whistleblower that notices. So here the difference is that basically Truebit is safer, but it has like, so it's a different trust model, I would say, but it's not as generic, so it cannot be used for the same things. For example, if you want to execute like the generation of a random number on Truebit, there is really no way to do it. While on something like this, it's very easy to implement, like with the random data source. So the idea is that the off-chain computation data source provides the authenticity proof so that you can verify that the context was safe, the execution was safe, without executing it again. So it's a verification, but it doesn't require a new execution. So if you have a very complex piece of code, there is a huge difference, because verifying the proof takes like a constant amount of time, while executing the complex code is something very complicated. So if you have many nodes, it can be very computationally expensive. Also, there is no need to use like dedicated virtual machines, languages, or anything like this, as you can just define a piece of code in the way you like. I want to dive into gambling because, like it or not, on the mainnet, 80% of smart contracts are probably doing gambling. So what is the reason behind looking for external randomness? Well, it's really complicated on-chain to find reliable sources of randomness that miners will not be able to compromise or to somehow orchestrate. So typically, smart contracts trying to secure huge amounts on lotteries and things like this look for external sources of randomness. So one way to do it is like moving the random number generator outside and trying to get some kind of guarantees on the fact that the random number generator has been executed correctly. So let's check how it looks like with the old approach, like with the data fetching from a traditional URL, like random.org, which provides random numbers via an API, versus like the computation, like the off-chain computation. The difference is that in the first case, you will just specify the URL of the random.org endpoint, and you will need to trust the provider of the service. While in this case, what happens is that you have much more transparency, because you know exactly what's going to be executed. And what's going to be executed is displayed here. So you specify you want a computation, and this is like the base 58 encoded multi-hash of IPFS, where anybody can really fetch the archive and check what the archive is supposed to do. Then the authenticity proof will reference this archive and will claim that the result comes from there according to the attestation, like to Amazon, for example. So mainnet is mostly gambling smart contracts. that are leveraging external data, but on testnets, there is a huge diversity of projects asking for external data. So why? Well, one reason is the cost of gas, for example. So many use cases, turns out, they are not as valuable on the blockchain when the fees are so high. So one obvious solution is the one of following a similar approach than this one, and trying to keep on chain just the critical logic while moving off chain as much as we can. So this is just a random list of some projects that are using Oraclize right now, and some of those are using like the off-chain computation to do some post-processing, for example, of the data they get from the web API. So they get the data from the web API. They need maybe to aggregate something or to do some calculations, and then they just send back to the contract the final result. So the contract is basically just in charge of releasing the funds, of changing the ownership or something, or doing really a very small amount of gas of computation. So the gas consumption is relatively low. This means that once you move to an off-chain context, like the execution of a piece of the smart contract, what you have is that the smart contract on chain has to handle the payments, change of ownership, the administration, the upgrading logic, which is already a lot, and it also is able to handle the challenge of the proof. So if the off-chain code, which has been secured with a different trust model, within a different environment and so on, turns out to be compromised, what happens is that on-chain, you can have the verification of the proof will not pass, and there might be some collateral being wasted, for example. So I will show a couple of examples. So this one is not implemented, but really anybody could implement it. We will likely create an example, a public example to show this, but I think that if somebody is committed to try in like half an hour, it's doable. So the idea is that you can create a generic computation archive that can be used to delegate to an off-chain context the execution of a Solidity function. So why would you want to do that? Well, let's say that you have a huge contract, like many we have today, and you have some functions, think of the CryptoKitties one, which has some complex logic, or which is expensive, because maybe it needs to read a lot or write in storage, or it needs to do, I don't know, different steps, it needs to iterate over things, something like that. So in that case, what you can do is you define the code in Solidity, you call Oraclize with a computation archive, which will try to execute in memory from a node the Solidity function that you had defined on chain. Then you send back the result, you send back the authenticity proof. Verifying the authenticity proof costs a fixed amount of gas, which is likely lower than the gas you have to spend for the function itself. So it's 60,000 gas compared to whatever you had in the function. If it is wrong, you can fall back to the on-chain execution. If it's correct, you would have like spent much less. So this is an example Solidity code of how it will look like. You just define an expensive function. Well, this is not very expensive, but you can put whatever you like here. Then you just call Oraclize. This is like cheap execution of expensive function. Oraclize will somehow receive the instructions that, what you want to execute is this computation archive. This computation archive knows that the argument is the name of the function that will need to be executed. And then Oraclize will send you back like the callback, and you will be able to verify it. If it passes, then you're fine, and maybe you have like executed a very expensive function that would have costed 3 million gas or something with 60,000. If not, you just fall back and do it on chain. The same thing can be done also with a Bitcoin Lite node, or any other node, really. So you can define in the computation archive whatever you like. So it can be like something we have tested is an SPV node, like Multibit, or it could be Electrum, or whatever Bitcoin node you like. And you can use it to reference from Ethereum, like some Bitcoin content. So you can, for example, say, what is the, I will share the slides, so don't worry if you cannot read it. So you can, for example, say, like, this is a Bitcoin address. I want to check via this computation archive, via the SPV node, if the given Bitcoin address has some Bitcoins or not. And if it does, I will receive the authenticity proof, I will verify it, and I will use it to release a payment on Ethereum. So this can be used really to connect anything with anything else. So if we are interested in Ethereum, we can use it to connect any existing chain following the same approach in a very easy fashion and with the guarantee of those authenticity proofs. So since the previous presentation was about Raiden, I just wanted to mention that we are studying very closely payment channels. And while state channels are quite far away in the future, something like a smart payment channel, which I will explain in a second, is definitely viable. And with Oraclize, it will be easy to implement. So a smart payment channel is just a payment channel where there are some conditions which are relatively simple. So it's not a generic abstraction of the state, but it's just a verification of a condition. Like, I want a payment to succeed just if the temperature in Paris right now is greater than 10 degrees or something. So this is something definitely possible. I don't have time, unfortunately, now to dive into this, but feel free to come talk to me or to ask for a question. There are something we are doing to make the computation data source more agnostic. You can see it here. On GitHub, you find several examples working with this same generic computation technique. So this is the current status. So as you see, there are more than 400 public GitHub repositories that are using Oraclize. So these are just the public ones. And we have handled on mainnet 450,000 plus API requests in the last 2.5 years. So thank you for your attention. That's pretty much it for the presentation. If you have questions, maybe you have time for one, maybe not. Let's try with one. Thank you.